All right, ladies and gentlemen, so we're going to do this quick exercise to kind of understand case control and cohort studies and how you can analyze an outbreak in both ways, much like they did with the cyclospora. And I will apologize if you hear the toddler in the background. That's just how we roll today in pandemic world. So this is the problem. The problem is a new measles vaccine is out, but vaccinesarebad.com said it is not worth it because 2 children who were fully vaccinated got measles as part of an outbreak of measles in 5 children. John Doe Jones said that's almost half. And what's worse, it's that most of the unvaccinated kids didn't get measles. People should buy our supplements, complementary and alternative medicine, aka scam, instead of those vaccines. And so what you see all the time is that you see anti-vaccine people actually take a truth and twist it around. And without the statistical knowledge and the epidemiological knowledge, then you tend to kind of believe what they say without that context. And so we're going to analyze that context. We're going to analyze it here. And so here we have the 25 children on the left-hand side here. And what I've done is that I've separated them into either getting the vaccine, which are all the ones in green. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 here. It's okay. 20 that got the vaccine. And 2 more that got the vaccine, but they ended up getting measles. And so this is measles. And this is no measles. Okay, and then you have the 5 up here that did not get the vaccine, and they all ended up not getting measles. So that's 5. So let's put the 5 here. And then you have 3 who got measles and did not get the vaccine. So now I've given you the total number, which is 30. I've given you those who were exposed to the vaccine, which is 22. And so what I mean by exposed is exposed to an exposure of interest, not exposed to the disease. I'm not telling you how many got exposed to the disease. Maybe all 30 got exposed to the disease. But what I'm telling you is who got exposed to the exposure of interest, which is vaccination. How many did not get exposed? I'm telling you that as well, right? These 3 up here and these 5 over here, so that's 8. How many got sick? So the outcome of interest, measles. These 3 here and these 2 here, so that's 5. And how many are not sick? And that is these 20 here, these 5 here and these 20 here, so 25. Okay, and so when I'm talking about exposure, I'm talking about an exposure of interest. I'm not necessarily talking about exposed to a disease. That's something that a couple of you got confused in the previous quizzes and in the midterm, I believe. When I'm talking about an outcome, I'm talking about the outcome of interest. It can be disease, such in this case measles, or it can be, no disease. That would be another outcome of interest, right? All right. So we have the number total. We have the exposed, the not exposed, the sick, the not sick. And if you remember from the book, and this is adapted from a paper, a good paper that you can look for an even further explanation of how to do these things. If you remember in the book, when we do a retrospective cohort study, we are in the present and we look at things in the past. Same thing for a case control study, but there's a slight difference, right? And then for a prospective cohort, you are in the present and you're going towards the future. When we do a case control study, we in the present, we know who is diseased and disease-free. In this case, measles and no measles. And we go back and we separate the kids, in this case with the kids with the measles, in the case without the measles. And then we look at the outcome, in this case, vaccination. It's the exposure or outcome of interest, right? So look at how we did that. It's a little bit different than the cohort. We'll talk about the cohort next, but just know where the present is and where the past is.
Dad, can you fix the paper cup?
And again, I apologize for the kiddo. Okay, so this is a 2x2 table in a case control. And I told you guys, right? I told you that we have 30 people, so that's the total here. And in these 2x2 tables, we're gonna make these cells A, B, C, and D, which will make it super easy to calculate the odds ratio, which is our measure of association. Okay, so let's see here. Let's see, how many were exposed or had the vaccine and had measles? So how many had the vaccine? 20, and had measles? 2. So only 2 who were vaccine. 22 got the 22, and 2 were the ones who had measles. Okay, so vaccine and outcome 2. No vaccine. Let me erase all of this ink. Okay, no vaccine and measles 3. So no vaccine and measles 3, so that's a total of 5. And then vaccine and no measles. So vaccine and no measles, it's these 20 over here, right? And no vaccine and no measles is these 5. And then you make sure your margins add up. So 5 plus 25 equals 30. And 22 plus 8 equals 30. So we're good. We're good right there. So what are the odds of being vaccinated and having measles? That is 2 over 20. 2 over 20. What are the odds of not being vaccinated and having measles? That is 3 over 5. Over 5. Remember, odds is the number of times things happen divided by the number of times that they don't. The number of times that measles happens divided by the number of times that measles does not. Okay? And so we're going to do the odds ratio. The question is, what are the odds of measles given that you get the vaccine? And so who has a bigger odds, the vaccinated or the unvaccinated? So the odds in the vaccinated is 2 over 20. And we're going to divide that by the odds in the unvaccinated, 3 over 5. And if we want to label it, is A over B and C over D. And when you do the math like this, you just flip the denominator, and it's 2 over 20 multiplied by 5 times 3. Or A over B multiplied by D over C. And you can keep doing the math. 2 times 5 is 10, which is A times D, over 3 times 20, which is 60. I should have just written 60, which is 60, which is B times C. And your odds ratio is 1 over 6, or 1/6. And that translates to 0.17. And so you saw AD times BC. I could have just done that. 2 times 5 over 3 times 20. Done it really quickly without having to figure it out. This is doing it mechanically, and you gotta be careful with that 0.17. And so the answer here is that children who are vaccinated are 1 minus 0.17, which is 83. They're about 83% less likely. They have 83% less odds than those who are not vaccinated of getting measles. Okay, because that was the original question. Because that is the question. Now, if the question was, well, how much higher odds do unvaccinated kids have than the vaccinated kids? Then you do the reciprocal of this operation, and it's 6/1. And so they are 6 times more likely. Unvaccinated kids are 6 times more likely to get measles than the vaccinated kids in our data. If you look at the statement from the anti-vaccine people, they say that almost half of the kids who got measles, right? Out of the 5 kids who got measles, 2 of them were vaccinated. Almost half. That is true. They also say what's worse is that most of the unvaccinated kids didn't have measles. Out of the 5 and 3, out of the 8 unvaccinated kids, 5 did not get measles. That is also true, right? But we are ignoring the proportionality that out of 22 vaccinated kids, only 2 got measles. And so that is what we are comparing. That 3 out of 8 who are not vaccinated versus 2 out of 22 who are vaccinated got measles. Okay? And so you see, this is how we do the odds. Again, it's odds. This is not probability. This is not risk. This is not risk ratio. So remember that our odds ratio, odds of measles given vaccination, odds of measles given vaccination is 0.17. Let's move on to the cohort study, right? In a cohort study, we are looking, in this case, we're looking back. So we are looking back. Let's erase all this. And we are told, we find out that 5 kids have measles and 25 do not. And we go back to see how many of them were exposed to the vaccine and how many were not. In a case control, we start with the same information, but you saw how I did it. We went back to see who were exposed. Now with the cohort study, we are beginning looking at the overall picture, at who is exposed, 22, and who is unexposed, out of 38, and calculating some chances, and we set it up with a table. So again, it's the same numbers, 2, 23, and 5. 2, 23, and 5. 5 here, 25 here, 30 here, 22 here, 8 here. Now we have to be careful though, because if we label this as A, B, C, and D, and you just do it mechanically, if you do it mechanically, you're gonna get some things wrong. You need to think of what you're doing. And here I am asking you about the risk. And so the risk is not 2 out of 20. It is 2 out of 22, as I explained previously, and 3 out of 8. Right? And so the risk of measles, given that you're vaccinated, 2 out of the whole 22. The risk of measles, given that you're not vaccinated, 3 out of the whole 8. All right? So what is the relative risk, or the risk ratio? So it is 2 out of 22 divided by 3 out of 8. What do we do with math? 2 times 8 over 22 times 3, because we flip the denominator. 16 over 66. And that is 0.24. So your risk, okay, previously it was our odds of measles given that you were vaccinated versus the odds of measles given that you're not. Now it is the risk of measles given that you're vaccinated is 2 over 22 versus the risk of measles given that you're not vaccinated, 3 out of 8. Your risk ratio, or relative risk, is 0.24. So you are, 76% less likely, less risk, 76% less risk of measles given that you're vaccinated. You take the reciprocal of that, which is 66 over 16, and your risk of measles, given that you're the risk of measles given that you're not vaccinated, is 4.125, or 412%, or 13% if you want to be technical about it, higher if you are not vaccinated than if you were. Okay, you have to think these things through and look at your math, look at your reciprocals, because this is not that is a correct answer, but it's not the answer to the question that I was asking about. This is the question that I was asking about. So your relative risk of measles, given that you are vaccinated, is 0.24. And does it compare to odds ratio? Well, yes, it's less than 1. Because remember, a number divided by itself is 1. If the risk is the same between the two groups, you're going to get a relative risk of 1. If the odds is the same, you're going to get an odd ratio of 1. But if the odds ratio is less than 1, or the risk ratio, the relative risk, is less than 1, then you have found an exposure that is protective for the outcome. If the relative risk is greater than 1, the odds ratio is greater than 1, you have found an exposure that is associated with risk of the outcome. All right? This is how you do the math for these. Remember, risk is A over A plus B. And for the other group is C over C plus D. But you can't just plug in the numbers. You have to understand what you're thinking about, right? The table in the book might flip this, or might flip the outcome. It might flip the exposure, might flip the outcome. You have to know what you're being asked. Finally, let's do some quick math with the odds, just so you see how the chi-square works. So we saw, right, 223 and 5, 223 and 5. So we saw 5 here, we saw 25 here, out of a total of 30. We saw 22 here, we saw 8 here. So this is what we observed. What did we expect? So to do the expected, you see that 5 out of 30 is down there in the denominator. So 5 out of 30, which is 16%, or 16.6%. And 100 minus 16.6, 83.4%. And we know that we have 22 who got the vaccine, and we have 8 who did not. So we do the cross multiplication for this here. It would be 22 times 0.166, which is 3.652. You do 8 times 16.6, 8 times 0.166, which is 1.328, and then you do 22 times 83.4 to get this number, and 8 times 83.4 to get this number. So now we have our observed and our expected values. The formula for the chi-square test statistic is the sum of observed minus expected squared over expected. So for the top left, and we're going to label them A, B, C, and D again. And so for A, it is 2 minus 3.652 squared over 3.652. For B, it is 20 minus 18.348 squared over 18.348. For C, it is 3 minus 1.328. And yes, in grad school, we had to do all these by hand. to make sure that the computer was correct. And you would say, well, what's the use of having a computer if you have to check it by hand? You don't have to do that all the time. You just do it once in a while when it's simple or you're bored, because you might find that somebody wrote a program that is not accurate, and you get paid money, actually, in some situations, to let them know, because they would like to know when their product is not good. Okay, so let me do the math and then I'll get back to you. Okay, so I did the math for A, B, C, and D. If you were doing this at home, you will see that a lot of the numerators were right around 2.7. And that is not a surprise. It shouldn't be a surprise. Your absurd minus expected should be about the same. You're just squaring it to get a positive number. But anyway, that's just one of those weird things that you see in these things. Don't worry too much about it. And so then you add, right? This is the addition of all of those: 0.75, 0.15, 2.10, 0.42. I'm gonna double check this 2.10 because that is kind of a deviation. So 3 minus 1.328, 1.1672 squared, 2.79. So that checks out with what I was saying before. It's about 2.7 something divided by 1.328, 2.10. Okay, and then 0.42. So you add these up, you get 2, 8, 9, 10, and 4 is 14. 3.42 is your chi-square value. And so what does that mean? What that means is that the chi-square distribution looks a little bit like this. And it's not a normal distribution. It's a little bit like this. A long tail. Like everything else, and this is 0 here. It's not centered at 0. It's 0 over here, and then goes to infinity over here. There is a certain point here at which everything to the left is 95% of the area under the curve, and everything to the right is 5% of the area under the curve. And we want to hit that sweet spot of 5% because that is the significance, the p-value of 0.05. And the shape of the chi-square depends a lot on the degrees of freedom. The degrees of freedom for this chi-square is number of rows minus 1 multiplied to the number of columns minus 1. And we have 2 rows and we have 2 columns. 1 times 1 is 1, so 1 degree of freedom, and that's how you get the shape. And with 1 degree of freedom, the critical value, we call it the critical value, at which you have 5% to the right, 95% to the left, is 3.84. If what we calculated before ends up somewhere here, so left of the critical value or less than the critical value, the probability of it being under the curve is about 95, or is more than 5%. Is less than 95%, but more than 5%. So the p-value would be higher. The p-value would be higher than 0.05. Not statistically significant. There's too much of a roll of chance in it. If it ends up being somewhere on the right, over here, then the p-value is less than 0.05, and we have a statistically significant observation. So what did we get? Well, we got 3.42. Darn close to the 3.84. And the p-value for that would be about, I know that it is already greater than 0.05, but it is about, according to R, is 0.064838. So it's not statistically significant. What you're seeing on that table has a very good probability of being just by chance. So how do you explain then the results? Because we're doing this as a odds ratio with a chi-square what was it, 3.4, and the computer's giving me 491, which is fine because I rounded up, and that's why it added up to 3.4 something. But the p-value of 0.0648, blah blah blah. So this is how I would present this in a scientific book or a scientific article. I would say the odds ratio of those who were vaccinated to those who were not vaccinated is 0.17 with a p-value of 0.065. The results are not statistically significant. This observation of 2 and 20 and 3 and 5 respectively in each cell, or 2 out of 22 and 3 out of 8 for this particular outbreak is influenced. There's a good probability that it's influenced just by chance. That just chance alone is what gave us these numbers. And the thing about this is that we're only dealing with 30, right? If we multiply all of this by 100, it changes this significantly. The odds ratios stay the same. The chi-square changes. And why does it change? Because if you start multiplying all of these numbers by 100, you get zeros after this. You get this moves over a couple of decimal values, right? And when that starts happening, then this number is going to get inflated. And when that number gets inflated, the chi-square gets bigger. And when the chi-square value is not 3.42, it starts getting bigger. It's going to cross the threshold of 3.84. That is called p-hacking. That is why when you see a study that doesn't quite reach statistical significance and they say we need more people in the study, it might be because they want to push that value to be under 0.05. Is that ethical? Well, I mean, it's not unethical, but it is trickery. These things, especially case control things, especially things that happen randomly, outbreaks, that you have no control over, or rather you have control, but they occur in nature. You don't want to go back and then start playing with the participants. Oh, I'm going to go back and find more cases, and I'm going to go back and find more controls so that I can reach statistical significance. No. You use other techniques like what we see in a long-term cohort study, what we see in a randomized clinical trial, where you mess around with the participant numbers. Those are experimental. In these observational analytical studies, you leave it alone the way it happened. But in the experimental ones, yes, you can increase the number of people that are in there, but you have to then use different statistical analyses for that. Logistic regressions, linear regressions, etc. For this outbreak, the association between vaccination and outcome very strongly towards being protective for those who get the vaccine and not so protective for those who didn't get the vaccine. And it is just by chance that we are seeing this, or rather there is a 6% chance that it's just by chance that we are seeing this. That's the caveats to this. So, for you to think and ponder, why was there an outbreak of 20 over 25 of children who were immunized, given that you know what you know about herd immunity threshold and measles R naught of 16? Why do we use odds ratios for case control studies instead of relative risk? And I explained that. Remember, you have control over what? You have control over the case definition, right? We control the case definition, and if we control the case definition, we can control who's a case and who's not. And so that's why we need to use odds ratios. If we were not controlling who was a case and who was not, as we do in cohort studies, the whole cohort begins, right? And we just follow them along to see who was exposed and then who later developed the disease. Then we use risk ratio. How do you explain that 2 of the 5 kids with measles were vaccinated? How do you explain that 2 of the 22 vaccinated kids got measles? Okay. How do you explain that? So these are the kind of things that we have to do in the health department. We have to explain these things when there's an outbreak of measles, of whooping cough, of chicken pox in a highly vaccinated classroom. Just think about this group as a classroom, right? A classroom of 30, and we have an outbreak of measles, and the parents are saying, hey, 2 of the 5 kids with measles are vaccinated. That's a lot. What's going on? The vaccine doesn't work? Well, yes, it works. And we saw it in the numbers. It's just, chance is messing around with this, as you saw with the p-value. And the proportions are what matters. 3 of the 5 who got measles were not vaccinated. 5 of the 25 who don't have measles are unvaccinated. the proportion leads to understanding of the vaccine as being a protective factor. And understand in the tables, who are you putting as exposed to the vaccine, exposed to the outcome of measles. All right. If you have any more questions, please feel free to comment, put it in the discussion forum, or get a hold of me, and we can talk it even further. Thank you.